Okay, so congratulations for sitting through my bait and switch, which was the discussion of block encodings during a conference that's supposed to be about Hamiltonian simulation. We did not talk about Hamiltonian simulation at all so far. What I'm going to do for the remainder of the time is talk about how we can use these ideas in order to be able to do Hamiltonian simulation. And then, depending on how much progress we end up getting through, I'll introduce some ideas that are used in order to be able to manipulate block encodings, specifically ways that we can use linear combinations of unitaries in order to be able to modify block encodings, and hopefully introduce the idea of the quantum signal processing, which gives you an alternative way that you can apply transformations on it. But as before, even if we don't get through my grand dreams of the many things that I'd like to teach you during this, I still would prefer to teach you guys a limited set of things that you can walk away with afterwards, rather than touching all of the topics. So please, interrupt me, stop me. I want to make sure you guys get whatever that one thing is that you're going to take away from this. But before I continue, there were some people who didn't get an opportunity to ask any questions before we had to take the cookie break. Does anybody have any questions before we get started again? Nope, cookie coma is setting in. Rad. All right, so now for something completely different. By the way, is Monty Python still in? Good, because I noticed with some of the Gen Z kids in my class, I was making a bunch of Holy Grail references. Nobody got it. It was like dead silence. So I'm glad that, that still, right? Like, there are still some people who understand the Knights who say me. Okay, so let's take a step back. And I want to say a few words at a high level about quantum simulation and how this can end up coming in to the formalism of block encoding. Okay? So quantum simulation itself is actually a very loaded term. There's a whole bunch, when somebody says to you that they're in quantum simulation, they may mean a whole bunch of different things. And when they say they do quantum simulation, they might mean a whole bunch of different things either. So quantum simulation can mean, for some people, tensor network methods. It can mean ways of you simulating physical systems on classical computers. Other people, when they say that they're doing quantum simulation, what they want to do is they want to be able to solve a problem like the following. They would like to be able to find they would like to be able to solve H psi equals E psi. And what they would like to be able to do is they'd like to be able to find the minimum value of E associated with it. This is what would be known as the electronic structure problem in chemistry, finding the minimum energy configuration that you could potentially have for a series for electrons that are interacting. So this is one notion of what we end up meaning by quantum simulation. But people more in the quantum computer science side of the fence, when they usually say quantum simulation, they mean something kind of different. What they end up meaning is they mean something like the following. They mean implement e to the minus iht for some specification of a Hamiltonian h over here. And based on a number of hands, I think most people know what a Hamiltonian is. Anybody doesn't know what a Hamiltonian is? Okay, anybody doesn't know what a Hamiltonian is and is not brave enough to put up their hand? That would have been a contradiction. So that's probably why. You guys understand logic better than I did. So, okay. So this is what we end up meaning. Now, let me give you the standard diagram of what I view as the computational problem of Hamiltonian simulation is from this perspective. The idea basically is what we have over here is Hamiltonian simulation, from my perspective, takes place in two worlds. We have over here the Hilbert space of the model, and we have over here the Hilbert space of the simulator. Okay? And what we have is we have some initial state that we prepare, or that we want to simulate in the model, and this state will evolve to a final state over here, psi of t. in the Hilbert space of the model. Okay? And what we mean then by quantum simulation is a quantum simulation involves a mapping that you end up getting. Specifically, it requires a bijection between a subset of states inside the simulator Hilbert space and the original one. Now, I say subspace for an important reason. The reason why is that our simulator need not have as many qubits as the system that we're actually simulating. There may be reasons why we might want to calculate some values in between inside our simulation algorithm. So the vector space that we use in order to be able to describe our simulation might be larger than the system we're trying to simulate itself. That's why I drew it ridiculously larger. I wanted to emphasize the fact that, in general, the simulation is going to be actually a bigger, more complicated thing than the system that is trying to simulate. So first thing that we need is we need to build a mapping between the initial state that we have over here and some state, I'll call it psi tilde of 0, inside the Hilbert space of the simulator. Then what we need to do is we need to find a discrete set of gate operations that will map our state to some final state over here, which I'll call psi tilde of t. And this state we want under this bijective map that we have between the subsets of the two states to transform into some state in the Hilbert space of the model, phi of t, such that the Euclidean distance of psi of t minus phi of t is less than or equal to epsilon for some epsilon greater than 0 that's specified as in the problem. So our task is then to do precisely this. Now, I want to emphasize this for one really important reason. The important reason is that this simulation problem actually is kind of very different than what you might end up getting if you ended up doing, say, some time-dependent mean field theory or something like that to simulate the dynamics. The reason why is heuristic approaches like this do not solve this computational problem at all. The reason why they don't solve the computational problem is the important bit about it that makes this distinct from most classical algorithms is the fact that we insist here that the distance between the simulated quantum state that we get out after remapping it to the original space and the ideal state that we would measure in that Hilbert space is provably less than or equal to epsilon for some epsilon greater than 0. And heuristic methods like density matrix renormalization group and more generally tensor network methods are very good at providing us with heuristic and often very accurate estimations. They really struggle at giving us provable guarantees about how accurate the results are in the end. So from that perspective, even though they're useful, they may not actually be solving this computational problem that we're referring to here as a simulation problem. Yet quantum computers can solve this for large families of Hamiltonians in polynomial time. Okay? So in classical algorithms, the only way that I know of how to do this in general is in exponential time. Okay? Now, of course, there's no proof in general that that there is an exponential separation between quantum and classical. Anybody who tells you otherwise wants to sell you something. Again, my apologies. What we do have is we do have a bunch of very, very strong plausibility arguments, going from exponential separations in query complexity to bizarre collapses of the polynomial hierarchy that we don't believe would happen. But these are all at some level kind of like implausibility arguments. So while we strongly suspect that there's an exponential separation between quantum and classical, it's very difficult to be able to actually show it in terms of gate operations. But now, at the very least, if we do something like this, we've got a specific computational problem that we would like to solve in order to be able to do this. Okay? So any questions about the setup that we have for our simulation problems and what this means? Rad. Okay, yes?
When comparing quantum and classical algorithms, task of preparing state is only the quantum, right?
So the question is, when comparing quantum and classical algorithms, kind of how do you incorporate the cost of preparing the initial quantum state?
Oh, maybe the results of the algorithm is quantum state is the quantum output, but classically what does it mean?
Okay, so from the perspective, so the question is, what does it really mean? If I wanted to talk about solving this on a classical computer, right, what would that mean? And now this is actually, unfortunately, that's a fucking good point. So the reason why this is good here is because of the fact that the classical algorithms you would normally think about using to solve this problem, like, for example, you could consider density matrix, like representing everything as a state, and then multiplying the state by a bunch of unitary matrices in order to be able to do it. Okay, so that's one way you could deal with it. But the output that you would end up getting would be literally a vector. Whereas in the quantum case, what you would end up getting is you would end up getting a quantum state vector coming out the other side that you would have to be able to extract that information from measurements. So the best way to actually think about this, if you want an end-to-end comparison, is you would want to change your computational problem to be one where your cost is now, say, to compute a particular matrix element, or to, say, consider the probability of one of the qubits inside the system being 1 or 0. And that problem can be turned into what's known as a promise BQP complete problem, which is sort of like these are sort of like the analog of like Turing complete problems for quantum computers. So that is the best way of computing it. If we want to take a look at the output, classical vector, like a deterministic vector that's representing this, nuh-uh, that's not a fair comparison. So you're absolutely right. Thank you. Okay, anything else? Cool, all right. So let's move on now to how we could do Hamiltonian simulation, okay? There's a bunch of different algorithms that have been proposed for Hamiltonian simulation. First one that was ever discovered was proposed originally, to the best of my knowledge, by Seth Lloyd, which is the Trotter-Suzuki simulation algorithm, which was one of your things that you could have heard me talk about if you had guessed it otherwise. But you didn't, so that's only in a different branch of the multiverse. That's one of the approaches. The next major family of approaches is a linear combination of unitaries family of approaches and a qubitization family of approaches. So let's take a look at how we would end up doing this using linear combination of unitaries / block encodings in order to perform the simulation. The most natural way of thinking about it is the following. Let's say that I wanted to do this evolution in here, e to the minus iht. Okay? What I'd like to be able to do, if I want to do this using the a block encoding, I'd like to be able to build, for a given value of t, I would like to be able to build a matrix that I'm going to call usim that will be of the form e to the minus iht here. Actually, I don't even need that, yeah. There. That would be my matrix. Now, I was bold and I put zeros here because of the fact that this is already unitary. Because it's already unitary, I know that all of my amplitude needs to be inside that top block, right? So this over here is looking kind of bonkers, right? Why the heck would somebody want to do this? So I'm telling you, all right, great. I want to build this unitary, right? E to the minus iht. And the easiest way you can do that is to build a larger unitary and put e to the minus iht in there. Why the heck would you ever want to do that? Any guesses? Yes?
You could like take a series expansion and then LCU it?
You could take a series expansion and LCU it. That's what we're ultimately going to do. But that is something that talks about how you could do it. It's not a question of why you would want to do it. The reason for why you would want to do it all boils down to the nature of the types of controls that you end up having access to. Here, by putting everything inside of a block, we can add matrices. We can actually multiply matrices. We can do all of our ordinary set of linear algebraic operations that we would want to have at our disposal if we were to do this on a classical computer. Whereas if we didn't build this inside the block, we're limited. I can't add together different things. Like, for example, let's say that I wanted to follow the proposed strategy for this. The simplest thing I could do is I could say, let's build e to the minus I ht, right? This is just going to be identity minus ht minus h squared t squared over 2 factorial, so on and so forth, as a series expansion. Cool, right. What's the first thing that obviously goes wrong if I tried to do this on a quantum computer? Well, first thing that obviously goes wrong is these guys over here. How do I sum these operations together? Next thing that obviously goes wrong is, okay, cool, let's say that I did have a way of summing those things together. I'd have to truncate this at some point. If I truncated it at some point, that guy ain't unitary anymore. So this is why, actually, even the most direct thing, the dumbest thing that you could possibly think of to do Hamiltonian simulation would be to do this, to do a series expansion. But it wasn't the first thing that people in the quantum computing community came up with. The first thing that they ended up coming up with were methods that went like Trotter methods, which would be e to the minus I h1 plus h2 times t. If each of these were Hamiltonians that I could brute force build a circuit for by themselves, then you use a divide and conquer strategy where you essentially say that this is going to be approximately equal to h1 e to the minus I h2 t over r to the rth power, and then the correction will be order t squared over r in general. Right? So then you can break this up into a series of short things. This was something that the community knew how to do. Why? Because it's only multiplying unitaries. It's not adding them. Until about 2012 or so, we didn't know the block encoding idea, which gave us methodologies for adding. So that's why, even though this is the very first thing that you would naturally think of in order to do it, because we didn't have a complete set of linear algebra tools yet in quantum computing, we couldn't even do this. But now we do have those. The linear combination of unitaries approach that I just taught you gives us a way that we can build such block encodings. Okay? So let's start from scratch, right? And let's say that we do want to end up building this type of a series expansion for our Hamiltonian. How could we do this? Well, easiest way in the world to approach this is to ask, okay, well, let's begin by thinking about how we would block encode a Hamiltonian. Okay? So let's say that we have ourselves an arbitrary Hamiltonian. Okay? We can always express an arbitrary Hamiltonian, as I mentioned, as a sum of unitaries. So without loss of generality, we can always write our Hamiltonian as the sum over I, alpha I, ui, for an individual set of alphas and unitaries ui. Okay? Part of the art for building a good quantum simulation algorithm, like I didn't say this is good yet, but part of the art of building a good simulation algorithm is picking a good set of the u's and also making sure that the sum of the alphas isn't terribly large. Okay? So this is what we end up doing with this. And I'd like to build a block encoding for this. So how can I build a block encoding for the Hamiltonian? Well, what I need to do is I need to do the following. I need to first build my circuit that will map 0 tensor n for however many qubits we need to the sum over j square root alpha j divided by square root alpha. And now I also need my select circuit, which will be equal to the sum over j j outer product j tensor uj for each of those guys. And then the LCU theorem that I showed was that 0 tensor identity over here times prep dagger select prep 0 tensor identity. Okay, this is equal to, by definition now, the Hamiltonian divided by alpha. So this gives us a way that we can perform a block encoding of our individual Hamiltonian. Cool. All right. So now the question is, what's the next step? Well, let's imagine what I wanted to do is I wanted to build a block encoding of the Hamiltonian squared. How could I build a block encoding of the Hamiltonian squared? Well, what I could do is I could say, well, h squared now is just going to be sum over I, alpha I, ui squared. Okay, so this will be the same thing as sum over I and j, alpha j, ui, uj. Now, if you were to characterize this over here as something, what would you call that? I don't know about you. I'd call that a linear combination of unitaries. Right? Because that's u times u, that's a unitary. Right? And now my weights are going to be alpha I and alpha j. So if I wanted to just build this guy over here, how could I do it? Well, easiest way to do it would be to do the following. To say, instead of just having one register at the top, now I'm going to have two. And what I'll do for these two is now I'll begin with prep. I'll have psi down here, and I'll do, this is notation again for kind of splitting in quantum circuits when I want to have a multi-register circuit applied only to two different blocks here. So I really just do this so that I don't have to like cross wires or switch or things like this. But this is the select operation going between those two. And then we've got the select operation going here. And then prep dagger, prep dagger. Now, we showed from the LCU lemma, right, that any linear combination of unitaries can always be broken up into preps like this. The prep that we have here for these amplitudes is clearly always just going to be the product of the amplitudes that we have here, which is exactly what we'll get with a tensor product between those two amplitudes on this side. So the tensor product of these two registers will give me, for each of those configurations I tensor j, it will give me the alpha I and alpha j corresponding to that. And similarly, this one, if we consider this register over here to be the I1 and this one to be the J1 here, this one is going to select the UI part of this, and this one's going to select the UJ part of it for any input combination of I's and J's. So this allows me to do this for the square. Now, if I wanted to do it for a cube, what do you think I would do? Exact same thing. What I would do now, if I wanted to do it for a cube, is I would just put in now another register at the top here, put in another prep, and now I'm going to feed this in to now another select going down here, and then unprep there. So in general, if I wanted to do this up to the kth power of this, I could totally do it for each of the individual terms. So cool. What this ends up showing is that each of these individual terms in the decomposition, I can build by, through a block encoding of this particular form. So if the only thing I wanted to do in the world was the squared, the cubed, the fourth term, all of those I could do. But unfortunately, what we need to do is a sum of all of these things. So how the heck could we do a sum of all of those guys? Any guesses?
Just stack them together like you have.
You can stack them together is the answer. Or another way of thinking about it is the following, right? Let's imagine that what we have is we have a Let's imagine what I had is I had a block encoding of two different matrices. I've got a block encoding of a matrix UA, which is A divided by alpha over here, and some junk that we don't care about everywhere else. And I've got another one that I have UB, which is B over beta now. A bunch of other junk here. What I'd like to do is I'd like to build a block encoding of A plus B. And so if I take a look at this, what would happen if I summed UA plus UB? Well, if I just summed the two together, what I would end up finding is I'd end up finding that this ends up producing A over alpha plus B over beta. Okay, and then question mark here. Okay, that kind of sucks. But what we could do is, what if I change this to summing UA over beta and UB over alpha? Okay, so now what I would have is I would have this be alpha over beta and beta over alpha. Now, combining these two together, what I end up with is I end up getting A plus, or actually, do I want to do that? Yeah, you know what, maybe let's stick with the original. Okay, let's deal with this, and if there's more problems than I'm anticipating, we'll figure it out. Okay, so if we have this over here, I have A plus B over these two guys. Then when I combine it, what I'll end up getting is I'll get A beta plus B alpha divided by alpha beta over here. And so, yeah, that's why I was saying that if I rejigged these guys to divide through by each of their corresponding values, then what I'll end up getting is I'll end up getting that this will end up going to A over beta over alpha, and then it turns out that this is just going to be alpha plus beta when I do the whole thing. So then, in effect, what this whole thing ends up going to when you simplify it is you end up getting a encoding that is going to be A plus B divided by alpha plus beta going in. So if we sum these two guys together, we can actually build a block encoding that is the sum of the individual block encoding constants. So what that ends up meaning here is that I can use LCU on the block encoding unitaries in order to sum together these individual values. So how will this end up working for the truncated Taylor series that we wanted to build? The way that this will end up working is we will have a series that will be of the following form. We'll have now our matrices that will be identity in a block encoding plus negative I H over alpha T. Then we'd want to put in negative H squared T squared over alpha squared, so on and so forth. And now we can use linear combination of unitaries to build this sum that we have outside of it. Further, actually, we can simplify things just a little bit. from this. And the way that we can simplify things is we can factor out t here, and then we've got a 1 over 2 factorial that I forgot here, but 2 factorial. So we can build this linear combination that we end up seeing of these guys on the inside. Okay? So this is now what we're going to do. What we're going to do is we're going to build a linear combination on the outside of each of these individual weights that we're putting together of those unitaries. So we're going to have now a linear combination of linear combinations, or a block encoding of block encodings, in order to be able to build this whole thing. Okay? And what this will end up looking like is, let's call this, I'm going to call this prep star up at the top, which will have the action that 0 over here will map to sum over I, square root of negative I over here, t divided by, sorry, I guess the i's will have to be included with this definition. It'll be square root I divided to the I divided by square root I factorial divided by some normalization constant I over here. So what we're doing is I'm building this actually pretty small register off to the front in order to keep track of each of the different terms that I would end up having, like the square term, the cube term, so on and so forth. Okay? And this will build my outer linear combination of unitaries that I'm going to then use the inner trick that I was describing for it. Okay? So when we do this, what is our combined linear combination of unitaries going to end up looking like for this? Well, what our combined LCU will be is it will be a circuit that ends up looking like the following. Show of hands, how many people know the term unary encoding? Okay, cool, awesome. So unary is the shizzle if you can do it. It is like the absolute best thing you could possibly think of for controlling, right? And, you know, the worst part about unary encoding is it immediately makes me think of Roman numerals, which causes me to think of the Roman Empire right now, which is something that I am mercilessly mocked about because I usually can't go more than about like 40 minutes before I start thinking about the Roman Empire, which makes me like the broiest of all bros. But we were talking about something more important. What was it? Yeah, cool, probably, yeah, something like that. So the overall circuit that we'd be looking at would be, let's imagine, instead of using a binary representation for this, we instead use a unary representation, which again goes kind of like Roman counting, right? So our unary representation would be 0 equals, I'll call it 0 sub u, and then 1 would be equal to 1 sub u. 2 now would be equal to 1, 1 sub u. 3 would be equal to 1, 1, 1 sub u. You get the whole idea. This is really nice because of the fact that we don't need to have complicated decodings for our control structure for it. We just need to control off of each of the individual bits in order to be able to say directly whether or not we want to apply this 1, 2, or 3 times. And why is that relevant? Well, the reason why that's relevant is that we need to figure out if we're doing a Taylor series expansion, we need to, in order to guarantee that we're within error epsilon for our simulation, we need to guarantee that if we do a sum from k equals 0 to capital K of negative IHT to the k, we need to guarantee that the norm of this difference is less than or equal to epsilon. So the question is, how large does this k, and this is over k factorial, and that's important. The question is, how large does this k have to end up being? Well, basically, what we end up getting is k factorial is equal to k to the k times e to the kind of like order k over here. This is the Stirling approximation. Okay? When you go through and take this sum over here and figure out what value you end up needing in order to be able to make this work, we end up finding that using the fact that norm h is less than or equal to alpha, the value of k that we end up getting for this ends up going like log alpha t over epsilon divided by log alpha t over epsilon, which comes from using a Stirling approximation on this guy and then solving for the remainder term that you end up getting in the Taylor series approximation. Solving for that remainder term being epsilon in a Taylor series approximation gives you a Lambert W function. And then once you go to the Wikipedia page to look up the asymptotics of the Lambert W function, you end up getting this result coming back in the end. So that's how that all works. And I hope that isn't the one thing you remember. But I guess learning that Wikipedia is a fantastic and amazing thing for all things mathematical is probably pretty good to know. I wish I could say the same thing about ChatGPT. It definitely is amazing. That is one thing that's true about it. I'm not sure about wonderful. I'm getting distracted. I probably need more caffeine. So, key point here is that the value of k is not very big. And so using a really uncompressed representation for the order of the term that we're looking at for the expansion isn't such a big deal. So if I do that, then my prep star circuit over here, I'm going to now assume that prep star will give me sum over I square root of t divided by I factorial I over here divided by some normalization constant. And this is I in this one hot unary representation. Okay? So we're just going to assume that we got that because otherwise I'd have to decode all the binary strings and the control sequence would be like way less than obvious when I'm drawing out the circuit. Okay, so now let's draw out the circuit that we end up getting for it. So what we're going to want to do is if we truncate at order capital K, I'm going to begin by applying a superposition over this, over all of the individual bits that we have for it. And I'm explicitly referencing the bits here for the input because of the fact that I want to show you the control sequence that ends up coming out for it. So that's the only reason why I've drawn 3 here, but I won't represent how many qubits are in the rest of it. So this is prep star over here. Then what we're going to have is we're going to end up having prep here. I'm going to have prep here. And let's just do this for the case where we're expanding this only up to k equals 3. Okay? So if I do that, then what I've got is I've got this being psi here. These are all 0 registers going in. What I'm going to then do is I'm going to now do a controlled select operation here, then a controlled select operation here, and then a controlled select operation here. Well, I guess I can just draw that as a single one, OG style. No, but it has to go through here, yeah. Okay, and now this will have to be unprepped for the theorem to hold. This will have to be dagger. This is prep dagger, and prep dagger. Okay? We can then see immediately what's happening is that this will apply. Each of these over here, we can see for every control sequence that we're looking at, if we have one, then only one action of the select is going to be applied. The other two are going to enter over here. If this was the only one that was 1, these two preps are going to sandwich and kill each other. They won't, because nothing will fire in between the two. So we can see that if this one's active, then we're only going to get a single preparation of the Hamiltonian. If this one and this one are active, then we'll get a preparation of the Hamiltonian from the first one and a preparation of the Hamiltonian from the second one, as I showed for this squaring business over here. Okay? This just gives us a cute way in terms of the control in order to be able to see how the individual ones are turning on and off for each of the orders. So we can see that the result that we get is if each of these guys over here is block encoding UH, using the LCU theorem, what we end up getting is that the result will be sum of I equals 1, or actually 0 to k, of negative I h t to the I divided by I factorial divided by alpha to the I. And now the reason why it's divided by alpha to the I is because we've got to remember that there was this normalization constant that we have in here. Each of these is normalized by alpha. So when we're summing together these powers of it, every time we apply one application of the block-encoded Hamiltonian, we have to divide by 1 power of this alpha. So that's why we end up getting this over here. Yes?
So you showed that when we want to add two unitaries, let's say U and V, so we want to calculate U plus V. So you showed that the circuit for the block encoding is one control operation on U and then another control operation on V. So let's say now it is H Hamiltonian plus the square root of Hamiltonian, H plus H2. Here it means K is 2. Okay? So that then that U is H and V is H to the power of 2. H squared.
So again,
that the
just
circuit is control of H and then control of H squared. So you're saying that this is equivalent to just adding a prep operation at the top.
yes. But let me recapitulate the question to the best of my ability. So the question at a high level is, okay, what we wanted to do is I wanted to sum together each of these different powers of the Hamiltonian, right? And what I'm kind of doing here is I'm not actually summing together each of these powers of the Hamiltonian. Over here, I'm saying, okay, if this bit is 1, then apply the Hamiltonian once. If this bit is 1, apply the Hamiltonian once. If this bit is 1, apply the Hamiltonian once. Okay? And my claim is that these are actually the same thing. The reason why is, let's just take a look at our encoding over here. If we wanted the 3 case, which is supposed to correspond to the cube of the Hamiltonian, we want to have 3 distinct firings of the Hamiltonian happening. Well, that's exactly what happens here. We get the first one triggering the Hamiltonian through the select circuit, second one triggering it, and the third one triggering it. And furthermore, this circuit that you see over here is actually exactly the same, right? And the only way that we can possibly get 3 and exactly 3 coming in that are touching my state psi is if this is 1, and this is 1.
Okay, so you're saying that when we're adding unitaries, if those 2 unitaries are dependent, then there's no need to add them. If those unitaries are like dependents, meaning H and H squared, because they're dependent, so I can, instead of having H control H and control H2, I can have an entangled state that can, okay.
So to recapitulate, what this is saying here is that if we were to think about doing the linear combination of unitaries naively, we might say, oh, well, what we should do is I should, directly block encode H squared. I should only, if I end up getting the squared term firing, apply the H squared. Then I should block encode the H cubed. And only if the H cubed term is firing should I apply the H cubed. But we can also see, looking at this, that it's a little bit more efficient to, instead of doing it that way, to just basically say, oh, well, H cubed is nothing more than H times H times H. So why not break it up like this, where we can kind of strip apart these different select circuits and kind of, bring together their common guts. So that way we're not repeating kind of the same thing differently for each of the control sequences. So it makes it a little cheaper.
I have another question. So now let's say I have an arbitrary U and V. How can I understand if there is any relationship between them so that I can simplify my block coding?
Okay, so if there's an arbitrary U and V, then there is no relationship between them, and you can't. That's easy. The thing is, though, often when we're dealing with Hamiltonian simulation, they're raised to different powers. And so here, there's a very strong relationship between it. If we were looking at the decomposition of the Hamiltonian, there may or may not be. And part of the art of coming up with a good block encoding for your Hamiltonian is asking whether you can do these sorts of things. Like, here's an example. Let's say that what I had is I had two terms. I've got x, z, 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 x, plus y, z, 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 y. These, by the way, for chemistry aficionados are examples of one-body terms that you would end up seeing in a Jordan-Wigner decomposition of the Hamiltonian. So these actually do show up. One thing you could do is you could say, okay, well, if I wanted to build these two Hamiltonian terms in, I could control this sequence if the input, say, is 0, then do this, or do this if the input state is 1. Another way that I could do this is I could say, always implement that sequence. And if the input state is 1, then apply S here, and then S dagger there. See what I'm saying? And this means that we don't have to control all of the intermediate operations because they're common to both of the types of Hamiltonian terms that you would end up seeing. So that is an example of how you can use particular types of patterns inside and recognizing that sometimes terms in your Hamiltonian will just be basis transformations, for example, off of each other. And in that case, all you need to do is instead of encoding each of the terms with higher multiplicity, you just need to encode which the bases you end up meeting and use this to swap between those different bases. So there's a lot of art to this, and the years of optimization of the individual numbers that we've seen for chemistry simulation algorithms, in particular, a lot of it comes from precisely this type of thinking about how we can best play these tricks.
So I'm trying to connect the circuit to an algebraic expression. So let's say you're I plus h squared. Is it you're factoring out h from the h and h squared, so you have I plus h times I plus blah, blah, blah?
Completely. That's all we're doing here. We're just recognizing the fact that h squared is nothing more than h times h.
Okay.
So then we can use that in order to be able to factor and simplify our select circuit so that we're not pretending that it has to do something entirely different on the squaring term than it does on the linear term.
Okay, thank you.
Yeah, sure.
So at the beginning of your talk, you mentioned that sometimes the simulated Hamiltonian Hilbert space will be bigger than your original model one.
Yeah.
And here it seems like in both cases it grows with the time, like the order you want to approximate Taylor series to. Between the two you just talked about, with this simplification with factoring out h, does that change how the Hilbert space grows with time?
Not as much. It doesn't change the growth of the Hilbert space here with this encoding. At least that doesn't change it. What it does change is the gate complexity of implementing these things, because we don't have to, we can use part of the control information from the first application of the Hamiltonian to simplify the one where we'd apply the cube of it. And this ends up giving a quadratic improvement ultimately in the end for the cost. But the part that does end up impacting causing the space complexity to end up being dependent upon a time is this cutoff, k over here, and that. So the number of qubits that we're going to need to represent these times over here, we're going to need k qubits to be able to do this, and we're going to need k times the log of the number of Hamiltonian terms in order to represent all of those different registers down at the bottom. So as you can see, that's the biggest extra space that we end up needing for it. And it can be huge. In some cases, this we could, if we're doing a highly accurate simulation, we could have a single qubit simulation that we're carrying out. And the number of ancillas that we're using will be asymptotically greater than that. So in this case, if you're considering the picture, right, where we have this, we could have something more like that, right? Where the Hilbert space that we're looking at is ginormous compared to the Hilbert space that we want to simulate. But again, the whole point of quantum computers is that they make Hilbert space cheap. Having a vastly more space associated with this is not necessarily that big of a problem. And it's especially not that big of a problem for long-term quantum algorithms where you're going to need substantial space overheads due to quantum error correction in the first place. So in those settings, the overhead that you end up having from reducing your, say, your magic state factories that you need to execute your algorithm in a sensible amount of time can lead to actually less overhead than if you tried to optimize the simulation algorithm for space directly. But it gets complicated and it gets architectural when you start having to worry about these things. Key point is that this is one of those examples of it, where the size of the simulated Hilbert space, or the simulator, is vastly greater than the size of the simulated Hilbert space. Any other questions? Yes?
In the example you showed here, we used like 2 n0 cats for the h square. So I'm wondering if you need like a 2 select like sequence for h square, 3 select sequence for.
Completely. So then the question kind of is like, for those of you who didn't get the beginning of it, if we're taking a look at it, how many do we ultimately end up needing? If we're doing this in general for k over here being our cutoff, we are going to have k repetitions of these guys in here, and we're going to have k selects going down here. Because every select and prep combination that we're going to get will give us a different power of our Hamiltonian when we're carrying it out. So if we need to go up to order k for it, we're going to need k of these, and we're going to need k of those. Okay, but that's it. So.
Sorry, if I can ask a question. Yes, so we are talking about that you can actually correct some of the result, probably, if your prep is easy enough. So in this case, it seems like the prep star is easy. So can we actually correct in this case, like for the case that the first 3 registers didn't end up in 0, if that makes sense?
Yeah, it does make sense, but we're not going to need to.
Oh, because we can do oblivious amplitude amplification?
It's almost like you know what you're talking about. Yes, absolutely. So we're going to ultimately use oblivious amplitude amplification in order to save the day.
So I had a question that suppose if your H has 2-body or 3-body terms in that, so can you combine them using an LCU into like a single unitary that then you can apply, or do you need to do separate circuits for 2-body term and separate for 3-body terms?
No, you can combine the parts of the 2 and 3-body terms. It's just what ends up happening for the 2-body terms is one of the easiest ways to do it is to control on the second sequence of the terms that end up appearing in the 2-body terms. And so then you just have a flag that specifies whether or not it's going to be 2-body, and then it will just control the second part of the sequence and do one of the 1-body-like terms to begin with. So you can totally play games like that. But one thing worth mentioning is that the number of 1-body terms is so small that those types of optimizations aren't necessarily like hugely important. I should probably get back to the lecturing soon, but yes.
Okay, so yeah, my question is, so I was just curious, what's the benefits of using this control? Because the question is, so compared to other maybe more complicated control, and we're using this unitary encoding to do the control, but the idle error can increase.
Well, when it comes to using this unary representation for it, nothing's really changing actually, because these are just different representations of numbers, right? It doesn't matter whether or not I'm controlling off of the binary representation or if I'm controlling off the unary representation. In each cases, the correct sequence of firings that you can check will match exactly what you logically want in both the unary and the binary representation. The difference is that if I wanted to do this in binary, I'd have to have multiply controlled operations here. I'd have to count out how many different controls I would have in each of these different cases, and it becomes much more complicated. And so for that reason, just to make things simple, and it actually also reduces the number of gates needed in order to do it. Spending a couple of extra qubits in order to represent this very small register in unary rather than in binary is actually a really good idea. So the story that I would tell in general is there's no error going between the two of them, but if you've got a small vector that's representing the prep that you need to control off of, often you're just much better off representing those numbers in unary rather than binary, because the space savings that you have by switching to binary will not be equal to the gate savings that you end up getting from having vastly simpler control.
Okay, yeah, thanks.
Okay, so let me just go through and then spell out how the rest of the algorithm ends up going, okay? When we put this all together, the question is, what is the block encoding that we end up getting? The block encoding that we end up getting, once we put all these pieces together, will be U sim over here will be equal to e to the minus I h t plus some error order epsilon over here, divided through by, and this is over alpha, of e to the that's what we end up getting. Okay? Now, for those of you who were talking to me during the break, you can see immediately why this is going to be a major bummer. Because the block encoding constant that we end up getting is going to grow exponentially with the total amount of time that we're simulating. The success probability scales like the square of that guy. Yeah. So because it goes like the square, this means that we're kind of dead in the water. But there's something that we can do that's really kind of beautiful. And that is, we can use amplitude amplification to save the day. So what we're going to do with this is we break up our evolution here into a series of short time steps. Okay? I'm going to pick each of these time steps over here such that t equals 1 over alpha ln of 1/2. Okay? Why do I do that? Well, the reason why is that the success probability is given here. If I call this A, the probability of success we said is equal to psi A dagger A psi divided by the normalization constant alpha squared. This guy over here is approximately unitary. Okay, so this is approximately a unitary. So then this is going to be approximately 1 over alpha squared. Okay, which means that this success probability will be approximately e to the negative 2t over here. So if I plug this in, choose this to be my value of t, then this will evaluate to 1/4. Now, for those of you who've done quantum algorithms for a while, when you see success probability 1/4, some part of you should jump into your happy place. Because the success probability of 1/4 is amazing. Because what we can do is the success probability of 1/4 allows us to do amplitude amplification. And the way that amplitude amplification ends up working at a high level is, imagine that we end up getting two states over here. we've got a state up here, which is psi good over here. We got another one, which I call psi initial here, and there's a orthogonal line going between the two. And this angle over here is related to the probability of success. This angle theta is like something like the arc sine of the square root of the probability of success or something like that. But anyways, the basic idea behind amplitude amplification is we construct a unitary that takes the following form. The minus sign is irrelevant, but people always put it there because they think it's pretty. This goes like 1 minus 2 psi g times I 1 minus 2 psi I. Okay? In this case, it actually turns out that we don't need to reflect about psi I. All that we need to do is reflect about a subspace that contains psi I. This is, I don't have time to cover it, but this was proved by the oblivious amplitude amplification theorem. It says that when your block encoding that you're carrying out is implementing a unitary, then you don't need psi I to be exactly psi I. You just need to reflect about a subspace that contains psi I. And in this case, that subspace that we're looking at is flagged by all of these guys being 0 here, right? Because that's how that all begins. So we can reflect about a subspace such that all of those guys that we want to be 0 that defines our block encoding, if we reflect about those guys all being 0, and then we reflect about the output, which is all of those guys being 0, then we can end up carrying out the following sequence. We reflect then, in essence, first about the space orthogonal to psi g, which turns our angle theta down here, and then we reflect about the space that contains psi I, which will reflect this vector up here to an angle 2 theta. This means that the initial probability of success that we get before, it was sine squared theta, and after one iteration of this process, this goes to sine squared 3 theta. Okay, well, where is this going with 1/4? It turns out that for p success equals 1/4, then theta, it's one of those special angles where theta is just pi by 6. So if I put pi by 6 in here, I get 100% success probability. So by picking my time to be precisely these values, what happens is my success probability does something like this. It starts out really high at t equals 0, and then it goes down exactly at this point over here to 1/4. And then I stop at this point and I kind of boost it up to 100%. And then I let it fall back down, then boost it back up and fall back down. That's the whole scheme. When you put all of these things together and consider all the costs involved, the total number of operations that we end up needing in order to do it, and by operations I mean applications of these prepare and select circuits, the total number that we end up needing scales like alpha t log alpha t over epsilon divided by log alpha t over epsilon. And that is kind of amazing because of the fact that it gives you near optimal scaling. Linear scaling with t is the best that you could possibly do, it turns out, from the no quantum fast forwarding theorem. And this comes very close to saturating that. So this is an example of showing how you can use block encodings in order to be able to implement the absolute dumbest Hamiltonian simulation method in the world. Fortunately, there's a bunch of other things that I did not have time to cover when it came to block encodings. This showed that we can add and multiply block encodings together in order to be able to build more complicated matrix functions. But this isn't the only way of doing it. The quantum signal processing and quantum singular value transformation give you ways of implementing directly polynomial transformations using only a constant number of qubits, rather than this enormous number that we ended up requiring with this technique. So it's got some real dramatic advantages. There's other things that can be done using these paradigms, such as the qubitization approach, which takes a method that was discovered ages ago by Andrew Childs that builds an operator that has essentially almost the same spectrum to the Hamiltonian and almost the same eigenvectors. But then using these ideas of block encodings and transformations on block encodings, we can take that operator and transform it into e to the minus iht. And that gives us actually a provably optimal simulation algorithm that actually even it gives us the best scaling with epsilon, alpha, and t individually. So these ideas end up giving you ways of doing simulation more broadly. But I should mention there's a couple of other things that are very neat about this. By using block encodings, it gives you extra freedoms. Even if you're working inside the case of unitaries, it can give you more efficient algorithms. But it also gives you better ways of implementing things like differential equations, which are well beyond what we had before because we can do generic linear algebraic operations with that. This gives us a way of doing DEs easily. Furthermore, all modern open system simulation methods are based on these ideas as well. So simulating arbitrary CPTP maps that are described by Lindbladian, for example, we use these ideas in order to be able to do the same thing too. And this idea, well, it's simple. And I should mention, of course, obviously, its implementation is highly complex. And you could spend your entire career looking at optimizing it. But I hope, at the very least, this gives you the flavor of how you could do it and helps you understand how modern quantum simulation algorithms work. Thank you very much.
Thank you. All right, everyone, we're gonna break until 3:40. So it's a quick little break. Use the restroom, come back, and be seated.